start this recording. Okay. Make sure that one's all right. So you've got assignment 7, last assignment. I promise. Woo, you can do it. In fact, even though we won't have time to get through the example today, I'm confident you'll be able to finish this off. If not, we'll go through the example on Monday, which will be basically the same as this. So no worries there. Make sure you get your chapter 7 notes. Right here, Ty. All term, I've been kind of like, there's no time to cover anything. And then as soon as I started typing up the notes, I'm kind of like gaining time. So now, I don't know what we're gonna do with this extra time. I'll think of something clever. I don't know. But it's probably good because this is the time of year where I've seen everyone around at school today. It's just, they're just not here. And that's okay. I mean, it's a busy time, so I completely get it. But yeah, good for you for showing up to class still. But like I said, I get it. It's a crazy time. And it's getting warm out, so. Okay. Well, here's Zach. So like I said, make sure you get your assignment 6 in, and then assignment 7 is the last one. Woohoo. So, what was I gonna write here? No, that was for the other class. Never mind. So we're gonna start chapter 7, our last chapter. It's on regression, and what's really nice about and kind of fun about regression is we get to change gears, and we're no longer talking about confidence intervals and hypothesis testing. That chapter of your life is done. Well, not until the end of the course, but still, right? No more assignments on it. And so regression is kind of this fun thing that a lot of you have already done before. So regression is basically just lines of best fit, right? And so I don't know about you guys, but I remember in high school in physics, we drew a scatter plot by hand, and then they said, okay, now draw the line of best fit. So you just take your ruler and you just try to figure out where it is. There's more math behind it than that, but the idea is the same, right? You try to fit a line that's going to capture most of the activity that's going on your scatter plot, right? And things got kind of wonky in the lab, right? We had to do the regression lab first, but that's because it's so kind of, I don't know, intuitive, I guess, right? We've got a line, or we've got some data, we try to fit a line to it. That's basically all regression is. So you can do a couple of different types of regression, but we're going to focus on just 2 numerical variables, and then that'll be good for us. So first thing we're going to talk about is just correlation. Correlation is a word that we use just in conversation sometimes. I don't know, maybe me more than most, but right, when I say 2 things are correlated, just means that there's some sort of relationship between these 2 things. And so we're going to establish just some facts about correlation and then move into actually building this regression line. Remember from chapter 1 when we said, okay, well, if we have some sort of plot like this, we've got an x-axis, the y-axis, and let's just throw some points on there. Looks great. And what we said was that our response variable has to go on the y-axis, right? So the response variable goes on your y-axis, and then your explanatory variable, explanatory, it keeps erasing stuff. Explanatory. I like response and explanatory because explanatory goes on the x-axis, right? Makes it easier to remember. But I've also got a note here that response variables can also be called the dependent variable and the independent variable. As far as research questions go, right, and what you've noticed from the lab is if we've got something like this, then we've got a research question about our response variable, right? How does the response variable change with changes in the explanatory variable? So for our research question, typically we want to know how does the response variable change with changes in the explanatory variable. So the response variable is the one you're interested in, and then you've got explanatory variables, or potentially more than one explanatory variable. And you just want to know, okay, how do these things change together? So what we're going to do is we're going to make a scatter plot, which you've already done in the lab, right? We made a scatter plot. And in this case, the example that we're going to look at is the relationship between high school grad rates in all 50 US states and DC, and the percentage of residents who live below the poverty line, which is defined as income below $23,050 for a family of 4 in 2012. Not that important, we're just going to talk about the percentage in poverty, right? But just so we know what we're dealing with here. And then describe the relationship between the percentage in poverty and the percentage of high school grads. So there are times when it's not clear which one should be the response variable and which one should be the explanatory variable, right? And so in this case, I would argue that it wouldn't really matter, right? One's not going to depend on changes in the other, right? They're just related to each other. So in this case, I wouldn't say it's obvious that percent in poverty is going to be on the y-axis, but because it's given to us here, right, we know that the percent in poverty must be our response variable. And then our percentage of high school grad must be our explanatory variable. Just like when we had a histogram, right? So we've got a histogram and I ask you to describe it. Not the word I used, but I can't think of it now, right? But describe a histogram. So you have to talk about the shape, the center, and the spread. Same idea here. There's going to be 3 things that we have to talk about to describe this relationship between X and Y, whatever they are. And so you have to look at the form, and I got you to do that in the labs, right? Is a linear model appropriate, right? So does it look like it follows a straight line? We went ahead and fit a straight line regardless, right? And so we're looking for any sort of distinct patterns or visible outliers, right? Outliers are just extreme points, right? We're only going to talk about linear relationship or a nonlinear relationship. Okay, so we're just going to group them into those 2 groups. In this course, we'll only talk about how to deal with a linear relationship. So you better make sure that you have a linear relationship, or at least say that you have one before you make a straight line. And I'm talking more in terms of the assignment 7 and the final exam. You still have to tell me that, yeah, it looks linear. And next thing we're going to talk about is the strength of the relationship. I've divvied it up into just 2 groups, right? Either it's strong or it's weak. And essentially, if you can see some sort of pattern, we'll call it strong. You can throw in things like moderately strong or moderately weak if you want to, right? But I'm just going to be looking, is it strong or is it weak? Random scatter everywhere, that's a weak relationship. Right? But here, because we can look and say, okay, well, if I had to just take a ruler and fit a line of best fit, I know approximately where it would go, right? That means I have a strong relationship. If this whole box was filled with dots, then it wouldn't matter where I put my line, right? They would all do a pretty bad job, right? And so then you have a weak relationship. So as soon as you see some sort of pattern here, then you've got a weak or a strong relationship, sorry. And finally, you're gonna have either a positive relationship, right, where both of them are increasing together, or we'll have a weak relationship, or, oh my goodness, a negative relationship. It's been a long week already. A negative relationship where things are going down, right? As one is increasing, the other one is decreasing. So just over here, I'll just make a little note so you've got it. Something that looks like this is a positive relationship. Something that looks like this is a negative relationship. Pardon? Well, the slope will take it into account, but it's just the direction of the relationship. You'll see the slope takes it into account, but yeah, so they're correlated. Okay, so in this case, right, we have to talk about all 3 things, and I'm pretty sure, yeah, so on assignment 7, part A is 3 whole marks just for telling me, is there a pattern, and if so, what is it? Is it linear or nonlinear, basically? And then what's the strength, and then what's the direction? Should all have 3 marks in the bank already. 3 out of 23, that's pretty good. Pack up, call it a day. So here we've got a linear relationship. Because we can see this pattern, we'll say it's a strong linear relationship, and we'll throw in negative as well, right? We've got a strong negative linear relationship. Okay. Strong negative linear relationship. Okay. Just for fun, we can also do, instead of scatter plots, we can do counterplots. I've given you the code to make counterplots. It's a counterplot package in R. And so, of course, it's just replace the dots with cats. And don't worry, there's 11 different shapes of cats that you can pick from. There's the playing one, the laying one, the sitting one, the lounging one, I don't know, standing one. They're all in there. And then it wasn't until Steve told me, he walked by and he's like, hey, that's Nyan Cat. I was like, so what now? Don't worry, I'm all up to speed now. And I'm not sure how that passed me by, but I didn't hear anything about Nyan Cat. And I guess that's how you know you're getting old. So anyways, but now I've seen the video, don't worry. And so the code you'll need, and this is important, no it's not. You will have to install the DevTools package, but besides that, this code should all run. And there's a little bit of extra, like the par mf row is just to put the plots side by side, kind of extra. But you've got the multicat command, that's this one here, and then the rainbow cat command, or rainbow cats, sorry, over there. So if you want to, you can play around with that. But I don't know, it's just for fun. Yeah. No relationship. So, I may not have heard about NyanCat, but I did hear about Counterplots. And I feel like when they released Counterplots, the R community just went crazy. And they're like, well, we need more shapes, we need more colors, we need more Counterplots. Even people who are just kind of hardcore, and they're like, you shouldn't be obstructing your plots with things that don't contribute. Even they're like, yeah, Counterplots are pretty fun. So here we are. It did output this junk. You can just ignore. It's from the Rainbow Cats, and I couldn't figure out how to suppress it. So after about 20 minutes of trying, I decided, no, it's not worth it. Just keep it in there. So, most importantly, any questions about Counterplots? I probably have the answer. No, I probably don't. But anyways. Although I worked a lot with Counterplots yesterday to make these notes, so maybe I do have the answer. And I ran it, or I didn't run it. I got Steve to run this code exactly as it is, and he was able to run it on his PC as well. So works on a Mac, works on a PC. I'm only concerned because I had an emoji mishap last term, where I had emojis in your markdown file, because you can put emojis in your markdown file, of course. But the way I had it seemed to only work on Macs, which doesn't help when the school computers are essentially all PCs. But anyways. All right, back to business. So we want to have a linear relationship, especially in this course, right? Because it's what we're going to be dealing with, but also because it opens up a whole kind of bunch of tools for us to be able to use. And just like a lot of things in this course, yeah, we only introduce kind of the basics, but even more complicated scenarios like a nonlinear relationship can be brought back to a linear relationship, and then you'll know how to deal with it again, right? And so a lot of the time, right, these kind of basic scenarios that we're introducing here, they're the core of everything that's upper level, right? So even if you get a nonlinear relationship, you're just going to try to do a transformation, and we'll talk about that in a sec, to make it linear, and then you just model it with a linear regression anyways. Okay. But so, of course, if we have a straight line, then we can fit a straight line to model the data. We can talk about the strength and the direction of the relationship through the correlation. And we can measure variability, which we'll talk about later. But also, most importantly, is that we can predict future values using a linear model. So the whole idea of making a model, right, is to be able to predict future values, not necessarily outside the range of our data, but if we have things that we haven't quite observed, right, then we can use our line of best fit to predict values and what they might be. So like I said, before we kind of move too far away from linear, nonlinear, right? Let's just talk about what you might do if your relationship is nonlinear, right? So you look at something, you've got a scatter plot, and probably in the lab, I mean, we all had different data sets, right? But when you made your scatter plot, you might have had something that was clearly, right, a curve, not a straight line. We just went ahead and fit a straight line through it anyways. But if you have something that looks like that, you've got a nonlinear relationship. So, and the reason for that is because one or both of your variables are non-normal, right? So you've got skewed distributions. So a lot of the time, if you're talking about money, right, then you're going to have a skewed distribution just because we've got this, well, zero monies, and then everyone's kind of, let's talk income just for simplicity, right? So income you can make from 0 to, and then some reasonable number. And then there's these few people who make a lot of money, right? But that's what's making our distribution skewed. So if you have a skewed distribution for one or both of the variables that you're looking at, yeah, then you're going to have a non-linear relationship. So what we can do is, and I've got it kind of cryptic there, we just apply a transformation. There's lots of different transformations that you can do. The most common one is to take the log, the natural log, not log base 10. And a lot of the time that's going to straighten things out. Right? So if you've got this curve, if you take the log of one of the variables, then, well, the non-normal variable, it'll straighten it out, and then you can fit a straight line to your transformed data. The trick is once you've transformed your data, when it comes time to interpret your results, then you have to undo your transformation, which can be kind of difficult, right? So because the numbers that you're getting have to be untransformed, right, in order for us to be able to deal with them. And so that's why we're not diving into it here in this course, right? But just be aware that it can happen. It can happen to you. Okay. Any questions? The transformation stuff is more about me checking a box that says, yeah, I talked about it. Great, moving on. Okay. So going back to our scatter plot, right, we had to describe the relationship between our x and our y, just like we did with the histogram, right? We had shape, center, and spread. Now we've got, looking for a linear relationship. What's the strength of it and what's the direction? Just like we had the mean and the standard deviation as numerical measures of center and spread, right? The correlation is the numerical measure of the direction and the strength of the relationship. And I'm going to add in here, not that. The linear relationship. We can find the correlation for any relationship, but it's only useful for a linear relationship. So correlation, I denote it by a lowercase r. Some fields use an uppercase r. The reason I avoid uppercase r is because that's the name of the programming language that we're learning in the lab, right? Or some of you are done the lab, so done learning R. But anyways, so I just don't want there to be confusion. And also, I was raised on a lowercase r, so it's hard to shake that once you're in the group. So we use correlation. R. I guess makes sense. We've got double R's in there. C was probably taken. We run into that a lot. Something's already taken. Okay, we have to find a better letter. But, so like I said, depending on the context, right, you'll know if I'm talking about the software or the correlation, but for that reason, I'm just going to use a lowercase r. So to calculate the correlation, you would have to do this calculation here. Of course, R will calculate the correlation for you, not to worry about that. Or, more simply, if we have S sub x sub y, so S is a standard deviation. This is for x and y, right? So we call this the covariance, which is something that I'm going to give you. So I'll give you the covariance, which is SXY. Then we can just use SXY is the standard deviation, or we're over the standard deviation of X times the standard deviation of Y. So I will ask you to calculate the correlation, but I will also have to give you the covariance, the standard deviation of the X's and the standard deviation of the Y's. Right? So I'll give you all three of these things. I've got over on the side, right, to calculate the correlation, we'll need to know the standard deviation, or SXY, the covariance between the response and the explanatory variable. Again, kind of a big formula, not something that you have to be concerned with, but just be aware that there's a lot of math that could be done that we're skipping. So, I'll just make a note here. I will give you SXY, which is the covariance of the X and Y. SX, which is the sample standard deviation of X. And S sub Y, which is the sample standard deviation of Y. We've seen this lots before, right? As soon as we have two samples, right, an X and a Y sample, each of those is going to have its own set of information, right? A mean for X, a mean for Y, a standard deviation for X, a standard deviation for Y. And now we've introduced this covariance of X and Y. So for the correlation, there's some key properties that we have to keep in mind. So the correlation is a numerical measure of the strength and the direction of a linear relationship. So we're going to have negative values for the correlation for a negative relationship and positive values for a positive relationship. And then it's going to go between -1 and 1, where at 0, we've got the weakest possible relationship. So no relationship if the correlation is 0. And then as we move further and further out towards -1 or +1, depending on if you have a negative or positive relationship, you get a stronger and stronger relationship. So down low here, kind of budging into the example, I'll do a little illustration here. -1 to 1, 0 in the middle. Of course, between here and here, you've got a negative relationship. Between here and here, you've got a positive relationship. What I said was, okay, well, I'm just gonna say either we have a weak relationship or a strong relationship. Where I'm roughly gonna cut those off is at 0.5, so -0.5 and 0.5. So roughly around here at -0.5 to +0.5, I've got a weak relationship. Anything past, right, 0.5 to 1 or -0.5 to -1, those will be considered strong relationships. just as a rule of thumb. And that's all I've got in the bullet points there. So, all right. To give you an idea of what correlation might look like in terms of the graph, right? Remember, so this is the same scatter plot that I'll be using, right? The percentage of high school grads to the percentage in poverty. And we're given a list of candidates for our correlation, right? And so we're asked to pick, okay, which one is the one that you think that it's going to be? We know we have a negative relationship, so we already know that A and D, they're out. Because they're positive, so they can't be. A and D are out. So now we've got a choice between negative 0.75 and negative 0.1 and negative 1.5. Keeping in mind, right, that correlation can only be between negative 1 and 1, option E is also out. It just can't happen. Now we have to choose between negative 0.1 and negative 0.75. We said, well, because we can see this pattern, we're calling it a strong relationship. So for that reason, a correlation of negative 0.1, you wouldn't really be able to see, or you wouldn't be able to see any sort of relationship. And so because we're able to see this relationship, the correlation is negative 0.75. Woohoo. This also gives you a pretty good idea of what a correlation of negative 0.75 looks like, right? If we're thinking about here on the number scale, oh, sorry, negative, we're way out here. We would say that's a really strong relationship. Whereas here, when we first looked at it, you were probably waffling between, well, is it strong, is it weak, right? But a correlation of negative 0.75, this is what it looks like, right? A correlation of 1, or negative 1 in this case, would be every single point is exactly on the line. And so there's a lot of condensing that can happen, right? But even a correlation of negative 0.75, there's a lot of movement in there, right? But we know that's strong, right? So that's why I say, as soon as you see some sort of pattern, you can call it strong. How about in the next example? Which of the following has the strongest correlation? So, and the correlation, we call it the correlation coefficient sometimes. So closest to +1 or -1. So again, we'll just go through and look at these and say, okay, well, the correlation, what it's going to do is it's going to fit a straight line, right, as a line of best fit, and then see basically how many points are on the line or how close to the line are they. And so we've got this nonlinear relationship here, really strong nonlinear relationship. Right? But because it's nonlinear, when it tries to fit a straight line here, it's actually only going to capture some activity here and some activity here, but not anywhere else, right? And so the correlation actually turns out to be quite low. Here we've got this very strong positive relationship. Here we've got a weak relationship, I would say. Doesn't really matter where we put our line in here in this cloud. Yeah, we can see that it kind of goes straight across here, right? But there's a weak relationship. And then here we've got a strong negative relationship, but not as strong as here. So all three of these last ones are linear, right? But as far as the one with the highest correlation is going to be B. So one really important thing is correlation does not imply causation. And it's so funny because the first stats course I took, he turned into my supervisor later on, but he's a yeller, so he'll swear in class and he'll yell at the class, and he's just very emotional about this stuff. And so all of a sudden in class, probably for like 3 classes, he would just yell out, correlation does not imply causation. And it really drills it into you. But I'm not going to do that. But correlation does not imply causation, right? And so a lot of the time it's going to be tempting to say, okay, well, if 2 things are correlated, then one thing causes a change in the other. But that's not true, right? And so sometimes, especially if we're dealing with data that we're not quite sure of what it is, right? And so I do a lot of data analyses, and I mean, people send me data, and stats is stats. You can just do analyses. They tell you what you want to do, and you just go do it. And so you have to be careful if you don't know what your data, what's reasonable in your data, that you don't end up in a trap saying that correlation implies causation. For example, here we'll know that no, that doesn't make sense, right? So just because 2 things are associated, right? So you've got this pattern and you've got a high correlation, 2 things are associated, right? They're going up together, or one's going up, one's going down. It doesn't mean that one variable causes changes in the other. So it's reasonable to say that, okay, as the temperature increases, the ice cream sales will also increase. And so if someone tried to argue, though, that, well, all we have to do is just keep selling ice cream and then it'll be summer forever, we know that that doesn't make sense, right? So you want to be careful that you're not saying something like that about things that you don't know anything about. That makes sense, right? So you never want to say that, okay, well, this causes a change in this. No, there's a relationship here and there's association between these 2 things, but we don't know what it's linked to. Remember in chapter 1, we said the only way that we can establish a causal relationship is through an experiment, right? So experiments are the only way that we can say that, hey, this thing causes a change in this thing. Okay? And then I was worried because it's kind of hanging off the margin, but it printed fine. So, or at least the last time I checked, or the last batch I checked, it printed fine. So I'm glad. My little funny. So, any questions? So today it's going to be a lot of theory, but what you'll find, even flipping through the assignment, is that when it comes down to it, what you have to do is actually pretty reasonable. I don't want to say easy, but reasonable. Well, we have to talk about all this stuff anyways. So let's move into actually fitting the line. And the type of line fitting that we're going to talk about is least squares regression. It's the most common version. There's lots of other versions. I mean, people have to get their PhDs somehow. So you develop a new regression model, and it's not as good as least squares regression, but hey, you did a thesis. Moving on. Right? And so there's lots of other ways, but the most common kind of established way is least squares regression. And so what happens is, okay, we'll use our least squares regression line, or just our regression line, if you prefer. And remember, the whole goal is to be able to predict values that we haven't seen. Right? So using some value of x that we haven't seen, what's our predicted value of y? And so here, we've got our line of best fit, our regression line. But what you'll see is that basically none of the points are on the line, right? And so that means that there's error in our regression line. We call these distances the residuals, right? The leftovers, but you can also call them the errors. But as long as you're comfortable with either, you're safe. And so a point that's going to be this high up, right? So DC at this observed X, right? We have this observed value of Y. If we plug in that same X into our regression line, then we get this predicted value of Y. And so the distance between the two is 5.44. It's positive because it's above the line. Here we get a negative distance because the point is below the line. And so the residuals are just a way to talk about the error that we have from making our line. Right? How much did we not capture here? So the residuals are often denoted by E for error. Also, R was taken by correlation. See how that can happen. All right, and so E is the error, the residual, and it's just the observed Y value minus the predicted Y value, the distance between the two. Because of the way that we find our regression line, the sum of our residuals is always going to be 0. And so what we're trying to do when we're fitting this line is we're trying to minimize the distance from all of these points. Right? So the least squares regression line just tries to minimize the distance to each of the points. Okay. Just some background on why we use the least squares regression line. There's other options, right? So we want to be able to have a line of best fit. So a line of best fit, just like I said, minimizes the distance from the points to the line. Right? One way that we could do that is, well, we could take the absolute value, right? So any negatives become positive, and then we can add those all up, and then we can figure out, okay, well, which line gives the smallest sum? That would be your line of best fit. The one with the smallest total distance from all the points to the line, that's your line of best fit. But the least squares takes the residuals and squares them. Same idea, right? So if we square a negative value, it becomes positive, right? So even negative distances, if we square them, become positive. And then what we're doing is we're taking the sum of the squared residuals and we're minimizing it. Right? We're picking the line that's going to make that the smallest value possible. Why is this the most kind of run-of-the-mill regression, least squares regression? Well, it's the most commonly used, and that's probably because it's easier to compute by hand and also on a computer. So definitely back in the days when you had to do these things all by hand, yeah, you're going to want to pick the one that's the least labor intensive. Okay? And so that's going to be this one. But also, and this one is the most, or the more interesting thing, is that in a lot of situations, a residual that's twice as big as all the others, right, is often more than twice as bad, right? And so by squaring that distance, then you've kind of amplified, okay, well, this residual was really large to begin with, and now it's going to impact your regression line by even more. Oof. Do you guys remember y equals mx plus b? Equation of a straight line. So we're going to revisit. So the equation of a straight line most commonly is y equals mx plus b. I don't know why. bx plus a plus bx. You get the idea, right? Where the one attached to the x, that's your slope. And the one on its own is your intercept. For us, right, if we're trying to model a relationship for a whole population, again, we're going to go back to using Greek letters for the population. What we're trying to do is, I guess I'll come back and talk about y hat. But what we're trying to do is we're trying to figure out what the population intercept is, beta naught, and then what the population slope is, beta 1, right? So those are the parameters that we're trying to estimate, but we will find y hat, which I promise I'll talk about, is equal to b sub 0 plus b sub 1 times x. Same idea, right? We've got the parameters now. We've got betas, but for us, right, we're just going to be using sample information, so statistics, and so we've just got these b's to deal with. You'll get it eventually. Anyways, y hat is the predicted value of y. A little bit tricky because we just finished proportions, right, where we had p hats. P hat is a sample proportion. It's just going to be a matter of context, right? If you're working in regression, then yeah, y hat is going to be a predicted value of y. So here, this is your predicted value of y. And if you've got p's or q's, p hat, q hat, those are all proportions, and back in chapter 6. Right? So I'll never do a y hat in proportions. Right? Y hat will always be the predicted value of y. And I think that goes across the industry board. No one would ever use a y for a proportion, just because y hat is reserved for regression. So getting into the stuff that you'll actually need to do, right, from this section is we have to calculate the slope, we have to calculate the intercept, we have to interpret the slope and interpret the intercept. Okay? So the slope is b1. And what you'll find is that you actually have to find the slope before you can find the intercept. And I mean, you don't have to memorize that, because once you get in to try to find the intercept, you'll see that, oh, I actually need to find my slope first. And then you'll go back and find your slope and then your intercept. Right? So it's not something that you have to remember, but it'll just happen for you. But we have to start by calculating the slope. The slope is your correlation times the standard deviation of the y's over the standard deviation of the x's. It's really important that we don't have our x's and y's mixed up here, right? So you have to keep track of, okay, which is my response variable? Those are my y's. Which is my explanatory variable? Those are my x's, right? And so here, order matters, right? We can't use Sx over Sy. That would be a completely different number. Also, recall that R was Sxy over Sx times Sy. That was another one. So this one is another one that was not on the formula sheet that I initially gave you. You may want to add that on, or it's on here. Because I used to just do the correlation, make people do other stuff with correlation, but for now, you have to calculate the correlation, but I have to give you SXY, SX, and SY. So I will give you SXY, SX, SY, X bar, and Y bar. You only need these 5 things, right? Because we had to use SXY over SX times SY here, but then SY and SX make a reappearance, but we've already kind of used them to find our correlation, so those aren't new. And then let's just quickly jump down. I'll go through the interpretation in a bit here. But to find our intercept, you're going to use the mean of the y's, so y bar, minus the slope that you just found, times your x bar. And this actually uses I think it's a cool thing. So your least squares regression line, bless you, will always pass through a point where you've got x bar and y bar. Right? So there's one point on your graph, right? So you've got your x's, your y's. You can calculate the mean of your x, the mean of your y's. On your graph, you can plot x bar, y bar. And so just as a fact, your least squares regression line will always pass through that point. And so that's the fact that we're using to find our intercept here. Let's jump back up here. Right, so those are the calculations. Now, of course, we have to do some interpretations. Once you have your slope is technically for each unit increase in x, whatever your x is, we will see a slope, whatever your slope was, increase in the predicted value of y, whatever your y is that you're talking about. Right? So you're going to sub out x, the slope, and y in this interpretation. Right? So on the assignment, I have part whatever, find the slope. Part next whatever, interpret the slope. For each unit increase in x, we'll see a slope increase in the predicted value of y. I keep this setup, right? Even if it's a negative slope, right? So if the slope is -3, then I just say we will see a -3 increase, because a negative increase is a decrease. So I'm not going to bother trying to make that conversion, right? I'm just going to say here's a negative increase, because that way I don't have to think about it too much. If you wanted to, you could say a 3-unit decrease, right? But then you'd have to ditch your negative. Gets a little confusing. So you have to interpret the slope. The intercept, remember, is where your line is going to cross the y-axis. Right? And so that's going to be the predicted value of y when x is 0. Right? And so this part about x being 0 is important. So it's the predicted value of y when x is 0. So for our case, we're going to have to swap out our y and swap out our x. Charlene. Oh, sending a runner, I see. Okay. So these are the general interpretations, right? And so after interpreting the slope, I ask you, okay, now find the intercept, interpret the intercept, and so the intercept whatever you find. So say you find an intercept of 4, right? 4 is the predicted value of whatever y is when x, whatever x is 0. Sometimes I'll ask, is it meaningful? Is it meaningful? Meaning, do we care about the predicted value of y when x is 0, right? So really what we're asking is, can x be 0? If it can never be 0, then it's not that meaningful to know what the predicted value of y is, right? Whereas there are some instances where, yeah, we can have a 0 in there somewhere, right? If our x is, I don't know, stock returns, right? We can have negative returns, we can have positive returns. At some point there, we can have 0 return, right? Temperature, same thing, right? Temperature can cross 0, but there are a lot of instances where 0 is just never going to happen, right? So yeah, it's where the line crosses the y-axis, but really it's not that useful of information. For example, if we're just talking about a house and x is your square feet, not talking about lots, just houses, right? If I told you, okay, well, the predicted price of a house with 0 square feet, it's only $200, guys. Well, you're paying $200 for nothing. So is that useful information? No, not really, right? And so if x can be 0, then yes, it's meaningful, right? If it can't be 0, then it's not meaningful. Yeah. Any questions about that? If you're following along, you've already done up to part E of J. Pretty good. So you can even do part F, right? Which was what? Find, oh no, you're way ahead. You're up to part G already. Man, oh man, you guys are ripping. Part G you can do. And then H, construct the least squares regression line. That's going to be this one. This is your least squares regression line. What that part is just asking you to do is, okay, y hat is just going to be y hat equals, and then your v sub 0, whatever you found it to be, plus your slope, whatever you found it to be, and then x you just leave as x, right? So your x's and y's, say fluid, right? Because you want to be able to use this line to predict values of y, right? So you want to be able to take this line now and plug in any value of x and figure out what the predicted value of y is. Okay. So even without an example, I feel like this assignment might fly by. We'll go through an example next day, but you've got it. Okay, now some cautions about, okay, so predicting new values or predicting values of y, that's all fine, right? Once we have our line, and just as a note, if, say, you found the wrong slope, right, the intercept hinges on the slope, and then your least squares regression line hinges on both of those. If you found the wrong value, yeah, I'll dock marks there, but as long as you follow through and you use that value properly, right, I'm not going to dock you any more marks. Okay? So you don't have to worry about kind of, oh, I screwed up my slope and now it's game over. No, it's okay, just for that question. It won't be too good, but after that, you'll be fine. So, as long as we have a linear relationship, we can use this line to predict new values, right? And so what we're doing when we're just taking a value of x and plugging it into the equation is we're taking a value of x here, plugging it into the equation, and then it spits out whatever value of y it has there. Right? And so we want to be careful because here, for example, if we extend our line to all the way to a 0% high school grad rate, no one's graduating high school, is that meaningful? No, not really. There's never going to be a state where there's a 0% grad rate. And so now our intercept is way out here. We have a huge percentage of poverty, right? But what we have to remember is that this line is only built off of this data here, right? So it's only built off of these values of x, somewhere between 75 and 95-ish, right? And so it's really only valid for this chunk of high school grad rates. Okay? The thing about a line is, yeah, it just continues and goes and goes. Negative infinity, positive infinity, right? It'll just keep going. But what our job is okay, well, we built this line from this data, right? So whenever we're using the line to predict values outside the range of our data, what we're doing is we're extrapolating. Right? And so we're extrapolating beyond the range of our data. And as soon as we are, right, as soon as we kind of head into this territory, where no, we didn't build the line off of information from here. As soon as we kind of step over that, then our prediction becomes less reliable, right? So we've got these very kind of unreliable estimates here. They might be our best guess at what's going on, right? Sure, if we had a 0% high school grad rate based off of this, yeah, our percent in poverty would be close to 70%-ish, right? 68-ish. Okay. So sometimes it's going to be our best guess, right? Our best prediction, but it's not a very reliable prediction. Okay. So one kind of keynote here. There are actually very few relationships where even if we have a linear relationship for the chunk that we're looking at, right, very few relationships are linear for all values of x. So you don't want to make predictions far outside the range of x that actually appears in your data. For example, just pulled this from the textbook. Kind of a weird but kind of fun data set. So they've looked at the men's age at first marriage from the 1900s to just after 1975, 1980, let's say. Okay. And so blue dots, I'd say from 1900 to 19, throw a guess out there, 1940 something. Okay, right? Just kind of history and such. Right, and so we've got this really nice linear pattern if we were only to look at this data here. Right. Then something happened, right? Kind of all-time dip here, and then things just kind of took off, and now people are 40 or something. No. Right, but we've got this kind of interesting pattern going on. The thing, though, is that if we only had this data, right, we would have this beautiful line, great correlation, nice linear pattern, right? So we could say, oh, well, I'm confident in predictions from this line, right? So then you try to use it out here. It's not doing a very good job of capturing these guys down here. and definitely not anytime past 1975, right? If we tried to use this line here, even though it was a really good line, even here, I mean, it's not great, but it's in the ballpark, right? Doing kind of a bad job at predicting, but past 1975, things are going the opposite way, right? But we don't know that necessarily. Also, here, so 1975, 2019, I would guess people are being married off in the womb at this point, right? So it doesn't really make sense. So oh yeah, just to bring it home. Children grow really steadily, right, between the ages of 3 and 8-ish, right? And so you've collected data on this child's growth between the ages of 3 and 8, and you've got this really strong linear pattern. And so we can fit a really good line to this data. But same as ice cream sales, same as when we know something about our data, then it's easier to say, hey, that doesn't make sense, right? I shouldn't be doing that. But here, if we tried to fit a regression line, right, so we fit a linear model, and we try to predict their height when they're 25 years old, we would predict them to be 8 feet tall, right? It's just because we know something about how growth behaves, right, in humans. I think all animals, everyone, everything, no. Right, but we have this prior knowledge of, okay, well, we only grow for some amount of time, and then we stop growing, and we just kind of stay the same height that we were at then, right? And so, but again, if you don't know a lot about your data, then it's easy to fall into the trap of, well, I'm just going to use this line to predict new values, but you have to keep track of if you're extrapolating or not. Any questions? Oh. Let's just quickly talk about R squared. You've seen the R squared. We use the multiple R squared in the lab. There's the adjusted R squared. I'm positive there are other R squareds. Just as before, people have to get their PhDs somehow. Oh, I've made up a new thing. Oh, no, it's not as good as the old one, but still a thing. Oh, congratulations. Oh, thank you. That's grad school. But anyways, so R squared is just the square of the correlation, right? So despite it being a lowercase r moving to an uppercase r, oh, keep doing that. R squared is just the correlation squared. Okay. Which also means that the square root of R squared is the square root of lowercase r squared, which is just the correlation. One thing you'd have to keep track of, though, if you undid the square, right, because you lose the negative value when you square it, right? If you have a negative relationship, you would have to tack it back onto your r, but that's the only thing. Okay? So R squared is just a measure of how good of a job, so it's called goodness of fit. I'll put it on here. Measure of goodness of fit. And you can look it up. It's a real thing. I know it sounds made up, but goodness of fit is a thing. So R squared just measures how well your model is predicting new values, right? Directly linked to the correlation, of course, right? But now because we've squared the correlation was between -1 and 1. Once we square it, we don't have any negative values anymore, so now we're between 0 and 1. Right? And so R squared R squared, oops, I'll say is a proportion, meaning it has to be between 0 and 1. By definition, R squared tells us what percentage of variability in the response variable, so y, whatever it is explained by the least squares regression line on x, whatever your x is. Once you see percentage of variability, right, remember, so R squared is a proportion, which if you multiply it by 100, you've got a percentage. As soon as you see percentage of variability, you're going to think R squared, right? So here, percentage of variability makes you think R squared. It's going to be a long blurb, but then you just think, oh, do I have to calculate R squared? Right, which you could do if you have the correlation, you can square it and find R squared. Or am I giving you the percentage of variability and asking you to find the correlation? Those are the two ways it can go. So if R squared is the percentage of variability of y that's explained by the line, then the remainder, right, the remainder of the variability is caused by things that are not in your model, right? Things that you haven't taken into account, or just randomness in general, right? There's sort of, everything's random, right? So things we can't control. But if you have a low R squared, it's usually because of things that have been left out of your model that are contributing to changes in the y. Any questions? No. So like I said, next we've got this big example that we'll go through on Monday, but I think you've got a pretty good handle. You'll be able to do all these questions, but we will go through the example on Monday. I'll see you then.